we'll go to the next lesson.
So like you upload like 10, 9 videos daily.
Well, like today I'll upload
5.
I'll upload 5 videos today. After.
After that.
No, that's it there being saved. You see, its file size is increasing.
Yep.
Okay. We've done that. Dropbox, DIFC, physics, field, lecture 3, electric field potential. Got this?
Yep.
So fields, there's still a lot to do in fields. You know, we're only still talking about electric fields, but if people have studied this before, there's still magnetic fields, there's still electromagnetic fields, there's still AC/DC transformers and gravitational fields. So fields is pretty big, but then the good thing is the atoms section is not too big. And a lot of it's, you know, you'll be comfortable with in chemistry. Okay, so electric field potential. Okay, so you know when a particle's on the ground, when it's above the ground, it has potential energy. And even remember the formula, I would hope, which is for potential energy, mgh. Because a force is acting on it, it would accelerate, which would increase its speed, which would increase its kinetic energy. So therefore, at the beginning, the kinetic energy must have been stored as potential energy. The kinetic energy must have come from somewhere. So if I have this here, right now, what's its kinetic energy? 0. And then here, it's not 0. So must have been potential energy at the start to become kinetic energy later. So it had potential energy at the start. Make sense?
Mm-hmm.
Yeah. When a charged particle is between two plates, so if this is a positive and this is a negative, and then I stick a positive here, and it's not moving, what will happen to it? It will move.
Yeah.
So here it has kinetic energy, but here it did not have kinetic energy, right?
Yeah.
So it must have had potential energy from the field. The electric field must be given it potential energy. The electric field must be providing it with potential energy so that it can have kinetic energy later. Okay? For the same reason, a ball above the ground has potential energy because later it will have kinetic energy. So we understand the idea, I hope. And there is a force that's causing it to accelerate, and this force is from the electric field. Just like gravity causes it to accelerate. So therefore it has the same potential energy. So by comparing formulas, we could get by comparing ideas with gravity, we could get a formula. So let me show you what I mean. So in the gravity picture, and you might want to write this diagram down, it might be helpful.
2 pictures.
Yeah, 2 pictures. Okay, what's the force acting down here? mg. And what do we say the potential energy equals? mg h. Let me call that h instead of d. You know this. This makes perfect sense, doesn't it?
Yes.
Now let's look at the plate picture. That's a Q, okay? What's the force acting down here? The force in an electric field? No, electric field. Huh? QE, yes. Now, we're ignoring gravity in this picture because maybe the plates are actually lying vertically, or maybe we'll ignore gravity because the mass is so small we can ignore it. So in this picture, there's no gravity. Okay, so if you compare the two pictures, what do you notice? Well, we have a distance, or you can even, in fact, you can even call it H if you want, it doesn't matter. But I'll call it D just to make it different. So we have a height in both cases, don't we? We have a downward force in both cases, don't we? The force has a constant in it. What's the constant here? G. And what's the constant here? E. The particle has a value that's causing it to have more of a force. Here, if I have a bigger m, I have a bigger force. And here, if I have a bigger q, I have a bigger force. So by just a direct comparison of the situations, we can get the same conclusion, but just with different variables. So what do you think the formula for potential energy is? Q, E, and D.
Why D? Oh, sorry.
It's like the H. But there is one tiny difference here. We actually have a formula for the E, don't we? Because it's the plate. So what is the formula for the E? V over D. So if I stick that into the formula, I get PE equals Q V over D times D. So what happens here? The D's will cancel, and you get this formula, PE equals QV.
Would be equal to joules.
Huh?
Would the unit be joules?
Yes. Yes. Now you just need to be very careful here about the V. Please note. Please note. The V here is not a constant. I understand that there's a battery here providing the field. But the V here is not a constant, because if you look at this formula here, the V depends on the D. And in this picture, the D is the height, which is something that changes. Like, after all, if I put the particle here, will it have any potential energy? No. So the V in the formula has to be 0, because the Q is definitely not 0. So in other words, this V here, please be careful. The V is not the voltage of the battery. The V will start off at the beginning as a full V, like for example 10 volts.
Okay.
But if this particle is in the middle of the field at the beginning, it's not 10, it's 5. Okay? So if you want to be more careful to make the distinction in the formula, you could say PE equals Q delta V, if you prefer. It is not necessary. And in fact, if you want to, you can still just use this formula. QED.
If that's done, then it depends on the distance.
Yeah, like a proportion of the original distance.
Stephen, why did you connect between them? Like the MGH and like...
The only reason I did that is because what I'm trying to say is we already have a formula for potential energy from mechanics. By making a comparison, we can get a formula for fields. I could have just said, here's the formula, enjoy your formula. But I want to give you a reason why the formula is this. And my reason is you can see a comparison with mechanics. It's the same situation, just with different letters. But it's the same situation of a downward force. Okay, so if I go back here, the formula due to an electric field is QED. Now sorry, I haven't decided if I want to use small q or big Q, so sometimes I switch between the two. I apologise.
Okay.
You pick one and stick with it.
Thank you.
That's fine, so stick with that. Or QV. So these are the two formulas. Oh. Goodness sake, I changed my mind in the middle of the definition. And I called it H, but D, whatever. The distance. So have you got these two formulas? Yeah. Okay. And E is V over D.
Yeah.
And I already talked about this. You making a comparison between mechanics and fields. But if I just flick back here for a moment, look at this formula. The M is what? The mass. So this is a property of the particle, the substance. The Q is the charge. This is a property of the substance, the material. The height and the distance are both heights and distances. What's the G here? It's a constant of gravity. What's the here? It's in a field strength. Therefore, maybe the G is some kind of field strength as well. Find out later in the season. Okay? Yes? Alright, so we have these formulas, yeah? Yeah, okay. So, remember, and again I'll be repeating this with atoms. We have to be extra careful with our signs here because we have both positive and negative. So just remember with potential energy, if you're saying it's positive, you're saying, of course, it has potential energy, which could become kinetic energy. If the potential energy is zero, what are we saying about the particle?
It's moving.
It's more precise, please.
Even have potential have kinetic.
Yeah, but what? How?
Falling.
No, because falling would have. No. If it's it's on the ground. Huh? Yeah. Also, it's just that it's free. So if there's no potential energy, it could also mean because it's not in a field as well. And what is potential energy is negative? What does that mean?
It's going upwards.
No. Now, please remember, I actually copied this slide from a mechanics slide. You might remember it. Nope, it's gone.
It's going backward.
Gone? We've forgotten? Have we? No, really, have we forgotten?
Yeah.
Yep. It's trapped.
Oh.
If the potential energy is negative, we say it's trapped. So the equivalent in mechanics was when the person was under the ground in a hole. Potential energy is negative, they're trapped. You need to give it energy to free it. Yeah? Yes? Yeah, okay. Remind yourself of this, please.
No, I knew that, but I don't know how you relate it to the charge because how would it be under the charge?
Yeah, so what I'm saying is, if you have your potential energy as a negative, you are saying that it's trapped, which means you must be doing some mistake because, as you pointed out, how could it be trapped? Because if it's in the field between the plates, it has to be accelerating as a force. So this is all I'm saying, that because you're dealing with pluses and minuses, if your calculations give you a negative potential, you're saying it's trapped. And if you think that's wrong, check your signs. Continue. Also remember that h will be the distance from the particle to the plate it's attracted to. So here, if this plate is positive and this plate is negative and this is a positive charge, if I make this an electron, which way is it moving? Up or down?
Upwards.
Up. So the height would be this to use.
Towards the direction.
Towards the plate it's attracted to. So remember, the height is the distance from the particle to the plate it's attracted to.
Not the distance between the plates.
Not the well, it could be the distance from the plate. If it starts at the wrong plate and it's pushed to the other one, yeah. Okay, is that okay?
Yes.
Yeah. Do you feel like you need to make a note of this,
Yes.
KJ? Some note of some sort. Yeah? Done?
No.
Continue? Oh, goodness.
Have you marked pretty much?
No, I'm in the marking process.
Have you marked any?
I've done stuff, don't worry.
Can we know?
Maybe. Don't know. Hey, Fahad, you gave me so many pages I can't get the spine back on. I'm not really complaining, but
Should have provided them with
no, fine. Right, did you write that down now?
Yes.
For goodness sake.
Too many pages?
I'm gonna detach your appendix. Alright, next. Don't worry, you'll get it in time when I'm finished. Right, conservation of energy. You know what that is.
Yes.
So it states that the initial energy equals the energy at the end. So as a formula you have this. Please note. I'm sure you remember this from mechanics.
Mm-hmm.
But pretend like you forgot it and write it down again.
We are pretending that.
Yeah, pretend you forgot it. Because I know you didn't actually forget it.
No.
Okay.
No. I've got that.
Yep.
I've got that.
Okay. Now, since potential energy equals QV, Q is small.
Okay.
The units of joules is not really so suitable because it's such a small unit charge. It's usually like 10 to the minus 19, 20, something like this. So we often use a different unit that still measures energy called the electron volt. So 1 electron volt of energy is the energy gained when 1 electron is accelerated by an electric field on a potential difference of 1 volt. Now wait, before you write that down, I just want to draw what that means, okay? So if you look here, this is a positive plate, this is a negative plate,
Okay.
and if I stick an electron right here, what will happen to it? It will move up and strike this with kinetic energy. So this means here it had potential energy. If this is one electron and this here is 1 volt, we can say that it has 1 electron volt of energy. You could work out how many joules that is by using the formula, which we'll do in a moment, but electron volts are often used for these problems because they're more suitable size. But here's the formal definition which you will need for the exam. Okay? Got that definition? No. Yeah? Okay. So let's look at an example of this. What is 1 electron volt in joules? So we'll go to this picture here. This is 1 electron volt of energy. It's 1 electron in a 1 volt field. So, the question was convert an electron volt into joules. So what's the formula for potential energy? QE. Do we know the Q? We do. It's an electron, isn't it? And do we, let's see, it's number 23. And do we know the E? Oh, sorry, of course it is. QV. Do we know the V? We do. Do we know the Q? We do. So if I put in the two numbers, we get this. A tiny amount of energy is 1 electron volt. So 1 electron volt is the same as 1.6 times 10 to the minus 19 joules. Oh, okay. Yeah. Convert 1 joule into electron volts. So by using this answer, you could do that, because you only want 1 joule. So you divide both sides by 1.6 times 10 to the minus 19. And on the right, you get 1 joule. And on the left, you'll get 6.24 times 10 to the 18 electron volts. Yeah. So a joule is a lot of electron volts of energy.
The question was compared 1 joule to what?
Electron volts.
To electron volt?
Yep. Continue.
This is a bit different.
Yeah? Okay. 2 plates are separated by 2 centimeters and there's a voltage of 500 between the plates. An electron leaves the negative plate and accelerates towards the positive plate. How fast will it hit the positive plate at? So I'll draw what you have here. You have 2 plates and there's a voltage here of 500 volts. And this is the positive plate and this is the negative plate. There's an electron here. Sorry, there's an electron here, and the electron leaves and then hits the other plate here. And the question is, how fast does it hit that plate? Now, for these problems, you can ignore gravity because the mass of an electron is so small that the force from gravity compared to the field force is so small it doesn't, not worth considering. The force from the field will be many times bigger than the gravitation. It will be thousands of times bigger. So the gravity force can be completely ignored. The gravity force will be something like 10 to the minus 33. So it can be ignored when you compare it to the force of the electric field. So when it's here, it has potential energy. Then it starts to accelerate and hits the plate here. It will have kinetic energy. You know that the potential energy at the bottom will have to equal the kinetic energy at the top here. So you know a half mv squared must equal q. Oh, now we have to be very careful here. This is a half m velocity squared, but this is charge multiplied by voltage. So you can get that the velocity is 2qv over m square root. So if we put in the numbers, square root, twice the electron charge times the voltage, which is 500, over the mass of an electron, which is number 3. So if I type all the numbers in and square root my answer, I get a pretty big, so I should maybe divide it by 10 to the, make it megas. It'll be 13.3 mega meters per second. Well, that looks stupid. Let's make it look a little nicer. It'll be 1.3 times 10 to the 7 meters per second. That's how fast it will hit the plate. Okay, you got that one?
Yeah.
Okay, next one. An electron enters a field of potential difference 10 kilovolts. The electron accelerates across the field until it hits a proton at rest on the positive plate. The electron binds the proton and they move off together. How fast do they move off at? So I'll draw this one for you to explain it a bit better. You've got, again, it's the same kind of deal. You've got a positive plate, you've got a negative plate. The voltage here this time is much bigger. It's 10,000 volts. And you have your electron which leaves here, and the electron comes along and then it hits a proton and the two of them become one and move off together. So the electron leaves the negative plate, hits a proton on a positive plate, and they move off together as a proton-electron pair.
They hit the plate.
The electron hits the plate, and it hits a proton on the plate. and the two of them move off together. So the first thing you need to do, what's the separation distance? Do I not tell you? Let's make it 4 centimeters. Why the heck not? Okay. Right, so first, no, you do need to know the distance. So firstly, let's get the potential energy at the bottom. That's equal to QV, which is equal to, let me see, we put in the numbers. Oh yeah, we have to work out, oh no, I know the voltage. So when you put in the charge of an electron and the voltage of 10,000, you get 1.6 times 10 to the minus 15 joules. That will equal the kinetic energy up here. Kinetic energy is a half mv squared, and that should equal 1.6 times 10 to the minus 15. So we can get the V from this formula, because we know the mass of an electron. So if I do my answer, multiply it by 2, divide by the mass of a electron, and then square root the answer. The V, again, it will be a big number like it was last time. You get 5.9 times 10 to the 7 meters per second. Now, what happens when the electron hits the plate? It hits and binds with a proton. What type of problem is this? It's a momentum one. So what's happening here is you have an electron with this speed and a proton which is at rest. They collide together, and the proton and the electron move off together with a speed. I'll call it x. That's what we want. So conservation momentum says m1u1 plus m2u2 equals m1v1 plus m2v2. Here it's at rest, so that's gone. And here they've become one, so we only need one of them. So you have the mass of an electron, I'll write it as me, times the velocity. That should equal the mass of an electron plus the mass of a proton times x. Mass of an electron is number 3. So the number on the left I get is 5.4 times 10 to the minus 30, and then the number here is 1.67 times 10 to the minus 27x. So when I divide, x equals 0.003 meters per second.
30 or 38?
30. Okay? Yeah?
Why is it so small compared to the one of the electron before it hits it?
The mass of an electron is so small compared to the mass of a proton. It would be like a bullet hitting a person. You wouldn't expect a person to move so fast after the bullet hits them. Even though it was going very fast to begin with, its mass is so small compared to what it's hitting.
So if you use a shotgun.
Yeah, but if I shoot you with a shotgun, the bullet is going fast. After you are hit by the bullet, it's not like you'll be going as fast as the bullet backwards.
But this is a huge difference.
No, huge. Well, yeah, but the mass electron is thousands of times smaller than a proton. Yeah.
Can you move all of this? Is it accurate? It sounds like
detail on that question?
Yes, it is. Do you want to leave it as a homework? Because you know you're not going to do it as a homework.
No, I do it.
Will you?
Yeah.
For reals?
Yeah. Yes. I don't have anything to do tomorrow.
Alright.
Let's do it now.
I'm moving on. I'll give you 10 seconds.
Okay.
Go on.
Ready?
Yeah.
Oh yeah, sorry, let me just add in. What did I say that mass was? The distance I made up.
4 centimeters. 4. Let's put PS. The mass is 4 centimeters.
I was going to write PS. Yeah. There. Okay. But it's such a big question.
Definitely not doing that as well.
Hang on a sec.
Is it homework?
Yeah. I like update.
My slides, and do what I want with them.
We don't have that.
Huh?
Well,
What's your problem now?
didn't have coffee.
What time?
2 cups. I'll get a 3rd cup going home. Okay, so let's have a look at the homework.
Can I?
Wait. That looks better.
No.
Yes. Do we have physics tomorrow?
No.
No, we have a maths class
Just
tomorrow.
a minute, just one thing.
Oh, tomorrow's Friday.